Okay. Okay. Good afternoon, everyone. Good morning, Professor Emblom. Today we have privilege to have Professor Emblom here, and he is going to give us some insight about the advanced material forming. Myself, Professor Nick Hare from Penn State University, I would be moderating this session. So just to give you a little bit of background of Professor Emblom. Professor Emblom earned a BS in Aerospace Engineering in 1984 from Pass College of St. Louis University. Upon completion of his degree, he worked at various aerospace companies, initially as an aerodynamicist and wind tunnel test engineer. Slowly, his interest moved towards structural analysis, design, and failure analysis. He returned to school and obtained a MS degree in engineering mechanics at Cleveland State University, during which he concentrated on finite element analysis and metal deformation in manufacturing processes. After another stint as a lead engineer in an aircraft structural analysis group, he returned to academic at TUT, a Ph.D. in mechanical engineering mechanics at Michigan Technological University, where he studied with Professor Weinmann and developed closed-loop controls for panel drawing. More recently, Dr. Emblom serves as an adjunct faculty member at Michigan Technological University. He is the owner of Emblom Engineering, which consults on manufacturing and forensics engineering. In addition, he serves as an instructor at local university. Dr. Emblom was the Advanced Manufacturing Track Chair for the ASME International Mechanical Engineering Congress and Expo for 2019 and 2020. He was raised to the rank of Fellow of American Society of Mechanical Engineers in 2021. So, Professor Emblom, the platform is yours. We would like to learn about the case studies.
Okay. Well, thank you much for inviting me to speak before your conference. This is a great honor for me. I really appreciate it. And so the title of the paper is Advanced Material Forming, 3 Case Studies. So this is work that I've done throughout a number of years. Okay, and the very first thing I want to do is congratulate Chaitan. He was just recently raised to the rank of fellow of the American Society of Mechanical Engineers. It's been a great honor to work with him on various conferences, and it's been an absolute pleasure. So,
Thank you.
so a brief outline of what I'm going to talk about. I'm going to talk a little bit about my background. I'm going to talk about stamp forming and controls, microscale hydroforming of sheet, and then friction stir processing, and in particular friction stir extrusion that we've been doing at the local university and along with in conjunction with Michigan Tech. So the reason why I have pictures of airplanes is because airplanes are near and dear to my heart. I worked in the aerospace industry for quite a few years, and this was actually the first aircraft that I worked on as a engineer. So, as Jason said, I graduated in 1984 with a Bachelor of Science in Aerospace Engineering. I was planning to become an aerodynamicist, and I in fact did work as an aerodynamicist, working in flight loads, wind tunnel testing, and flight test from the initial part of my career. And later on, I started transitioning to structural analysis of aircraft, and then started working in finite elements analysis and discovered metal forming in FEA and the vast number of nonlinear FEA problems. And I fell in love with that. So in 1998, I moved up to the Upper Peninsula of Michigan to work to work on my PhD at Michigan Tech, and I met a Professor Klaus Weinmann, who at that time was very well known for as a metal forming researcher, and he gave me the PhD project of stamp forming and controls and mechatronics. So it hit every single note that I was possibly interested in as a research project. In 2001, I started teaching at UL Lafayette, and I also started a consulting business. And by the way, I was working on my PhD. And in 2003, because of legal requirements uh, for teaching senior level classes and design classes, I obtained my professional engineer's license for the state of Louisiana. And here's another picture of an aircraft that I worked on. I completed my PhD, and then Michigan Tech made me an adjunct assistant professor. That's a position I still hold today. And so, as a consequence, I go up on a yearly basis and collaborate with faculty at Michigan Tech. And in 2009, I established at my local university an advanced metal forming laboratory. The picture that you see here are when I had a stint at a small stamping company. I was doing finite element analysis of a number of these parts, certainly not all of them, uh, to help their production. So my first test case or case study was uh, actually partly for my PhD research, and that was to implement closed loop control during the stamp forming process. This has been around now for a few years, and various auto companies are actually implementing this now to improve their forming process. But the idea then, as it is now, is to improve the robustness of the stamp forming process to improve different components, especially the body panels of automotive. And we were trying to look at improving the formability of either high strength steels, thinner steels, and aluminum. And so my work focused on an aluminum alloy. So you can see a picture of what I was forming here in the lower left. We call that the racetrack die. It has semicircles on either end and then a straight region. And this is like one step more complicated than standard cup forming. And you can see over here that shaded area all along here. Those are actually grids that were used for measuring strain. And then you can see a quarter FEA model uh, over here, and you can see uh, uh, different paths from A to D. We use those to study the strain effects in various locations. So the press that we used had been previously converted from a single stage uh, rotary press where we had a flywheel. That flywheel was replaced with a hydraulic actuator. From the ram, we suspended a total of 6 hydraulic cylinders. Those were used to act as to generate blank holder force. We also had a punch with a custom designed load cell for measuring the total punching forces, and a flexible blank holder that was designed using FEA to minimize both wrinkling and variations in strain from location to location. We had uh, uh, an active drawbead system. Here's the drawbeads poking out of the lower tooling. And then it was connected to some hydraulic cylinders that were within the core of the press table that could raise up and down. So the tooling had quite a bit of instrumentation embedded into it, besides the total punch force that we could measure uh, at this load cell. We had local punch force sensors that were located on either end of the die, and plus along the straight regions in front and back for the punch. And we had corresponding local punch force sensors in the die shoulder as well. We also had non-contact proximity sensors along the edge here that they were located to avoid interference between the blank holder and the so we wouldn't and the tooling, and so that way we would not damage the non-contact proximity sensors. We also had the hydraulic cylinders for the blank holder force. They're numbered P1 through P6 here. Those were located based upon optimization study for minimizing wrinkling while at the same time minimizing the variation in strains, and also our active draw beads that could go up and down. So here's our draw bead that could be displaced up and down. Here's in the punch nose and the die shoulders, you can see our force transducers. They're actually capable of measuring both the flow in forces prior to entering the die, as well as the forces once the sheet has entered into the die. And we call the forces located here the local punch forces. Here's a picture of the sensor mounted within the die and an active draw bead that was controlled based upon this guide draw bead guide body located here. So we actually implemented 4 different types of closed loop control using the local using the local punch forces to control, as well as and controlling using either the blank holder force or the active draw bead. So I'm going to show you what happens with the local punch forces first. Controlled by the blank holder force. So this was the figure on the left. That was initially our first attempt at closed loop control. We picked a trajectory at random, so we did not actually select the best trajectory that we could, but we can still see that we got closed loop control. We did not actually start performing the test where we were implementing control until in this region here. And you can see that our local forces are quite high compared to our target. And so you see a significant decrease in the local punch, the local blank holder forces. We started increasing as the local forces dropped below the trajectory. We increased the blank holder forces, and you can see that eventually we got significantly high blank holder forces and then came down. But you can see that how the blank holder forces reacted to the measured local punch forces. And this was at the local force transducer that was near the draw bead. And we actually, by the end of the test, had pretty good agreement between our target force and our desired and our forces that we measure. So but it wasn't perfect, and we found that was extremely frustrating. We did end up improving our trajectory so that we could have better control. I should say that the variations in the local forces were limited because this is a fairly straight region, and so we're not able to get a lot of variation in our local punch forces because all that's going on is the sheet's bending and unbending. If we look at what happens at the die end when we control the local punch force using the blank holder force, we can see that we're a little more sophisticated. We start out with our trajectory starting down here. We implemented control somewhere around a draw depth of 10 millimeters. we had fairly decent control of our local punch forces. And you can see for our local punch force 15, which is in the punch nose at the die end, we track our target quite well. Now that's opposed to this signal here for the opposite side of the punch. And there we did not track well, but we did not actually control the local punch forces for this particular force sensor. So then the thing that I was really interested in doing was control the local punch forces at the draw beads. And so here you can see our desired target for the local punch force, and you can see that our draw beads are operating independently to control the two force sensors, which track our target quite well. So what's cool about this is that using a somewhat unsophisticated control scheme, it is that we could independently control the forces where the draw bead penetration for one draw bead would act as a process disturbance for the other draw bead. And so we were delighted with seeing the results for this particular test. And the last thing we wanted to do is, because wrinkling is such a big issue in stamp forming and is the cause for a lot of part rejections, we wanted to implement wrinkle control. And according to conversations we had with one auto manufacturer, a 0.2 millimeter wrinkle was cause for rejecting parts at that time. So we wanted to ideally control at 0.2 millimeters, and we tried it. And for our press, we could not actually control wrinkles. Once the wrinkles got to 0.2 millimeters, we could not stop them from being removed. So we changed our trajectory to much less than that, to like 0.01 millimeters of wrinkle, and you can see our wrinkles here that we measured. This is actually the maximum wrinkle anywhere in the press. And we actually start controlling the process somewhere around here. And you can see that we start decreasing the forces. And then all of a sudden, the wrinkles start growing a little bit. And so we have an increase in the blank holder forces. And then when our target wrinkle starts increasing, we have a drop in blank holder forces until we get enough compressive stresses around the edge of the flange that we start growing a fairly large wrinkle. And you can see the response of the blank holder force increases until we get an acceptable wrinkle. Then there's another growth in wrinkle, and we remove those, and then we start coming to the end of the test. So the takeaway of implementing closed loop control was that we could control the local punch forces using the draw beads quite well. We had a little more issue with controlling the local punch forces using the blank holder forces. It's more easy to do it at the die ends and in curved regions compared to along straight regions, such as where the draw bead is located. And we could also control the wrinkles if we judiciously pick the threshold wrinkle for controlling. So as much as closed loop control is really interesting, the bottom line is we want to make good panels and consistent panels when we're stamp forming. So the figure on the left is for the major strains and minor strains that were measured along path 8. That's in this region here. And 0.1 is way up here, and 0.7 is down here. And you can see that the strains look fairly chaotic. When we implement closed loop control, especially of the draw bead, you can see that, yes, the strains look somewhat chaotic here, but also it becomes difficult to pick these exact locations on the tooling, and so there's going to be some variations here. What's really interesting is that the strains on 0.7 here look somewhat random, but what we see here is that as of 0.6, we see to 0.6 to 0.7 that we have what appears to be convergence in our strains. And so that gave me a lot of hope that we were actually doing indirect strain control for our while we're controlling on local punch forces. So the other location that was really of interest to us were the die ends along path B in particular, because all the failures, all the tearing always occurred right along path B. So we can see that another useful strain path would be path D, which intersects path point B1. So I decided I want to plot to see what the strains did along path D and include D1. And they look like they're very good agreement, but then if you go back and look to see what the variation in the strains is, this plot ranges from about positive 50% of strain to negative 50% of strain. And so these strains are, the scale is deceiving us. So I went back and looked at just what's happening on D1 for open loop tests varying the blank holder forces and then the draw beads. And you can see that if I vary the blank holder forces, the strains tend to increase with increased blank holder forces, compared to what happens if I vary the draw, if I'm just controlling with constant blank holder force, but vary the draw beads. I can see along path B and D1 that the strains are relatively constant. So, okay, that means that I should be able to control the strains at the die end using blank holder force rather than draw beads. So I wanted to dial in more about with the different strain regions. So I looked at the strains, and here's an isograph of the strains near the draw bead. You can see that they tend to be relatively parallel, and that actually makes sense. This is in essence a very large strips drawing section, even though it's part of the larger panel that's being formed. And so right around here is the end of the draw bead. We can see once we get past the end of the draw bead, we go from uniform and parallel strains to interesting geometries of the strains for the major and the minor strains. And so it was time for us to take a look to see what's going on in the die ends. And so looking at what's happening along path B, we compared some open loop tests, which are shown here. They're hollow symbols compared to the closed loop test for varying lubrication conditions. And we can see that for the when the draw bead is at 8 millimeters, we actually had a failure. This was the highest strain that we actually measured, and it's close to FLD 0. And if you look to see what happens with the various closed loop conditions that were tested, you can see that while we might get very high strains that and somewhat closer to the forming limit, but it's still significantly below the strengths that were measured for open loop tests. And you can see some of the strengths were quite low compared to the open loop tests. Okay, so that was just along path B. So what happens if we look at an entire region, the die end? And this was actually done for these strengths were measured on the inside rather than the outside. These were measured at the outside. This was measured at the inside. So we can see generally that for open loop tests, the strengths tended to be higher compared to the closed loop tests where they tended to be much further from the forming limit. My next study is in sheet hydroforming, and I was interested in microscale sheet hydroforming because I walked by a poster at another university and I saw that they were studying microscale fluidic processes, and I said, hey, that looks like a really interesting process, but I'm really more interested in how we can make these microscale fluidic devices. And I said, hey, how about hydroforming or stamp forming? And I read a lot. There were a lot of people doing stamp forming at that time and dealing with the problems of stamp forming. I thought that hydroforming would be a natural fit, as indeed it's people have been started using hydroforming to produce fuel cells. And so I went back and talked to a student at my local university, and I said, hey, how about working in microscale hydroforming? And so here's a picture that you'll see later on of a 1 millimeter high pressure bulge test. I also had some undergraduate students work on fuel cell. And so this was their first attempt at making a fuel cell using their hydroformed channels for carrying oxygen and hydrogen. And that's the work of a PhD student who was interested in improving fuel cell manufacturing. So the problem with us and sheet hydroforming, especially microscale sheet hydroforming, is we did not have at that time a pressure system, let alone a high pressure system. We didn't have tooling available, and we didn't have any methods for measuring strain. So those are significant setbacks. But I always believe that if you're going to start something, start out as simple as you can, and then you can increase in complexity. And that's exactly what we did. So my grad students' first efforts at hydroforming consisted of this setup where we actually used a small hand pump. And later on, he was able to get his hands on a pressure intensifier because this has a very limited pressure. So we could multiply the pressure by 16 through this pressure intensifier. And then we sent the high pressure hydraulic fluid through the hose into our tooling and our dies. So this hose pressurized this this tooling here. Here's the orifice for the hydraulic fluid, and then we had this as the blank, and we had a hole that was 1 millimeter across. We also had a 5 millimeter diameter test section and a 11 millimeter test section that we tested. And some students rebelled against using that system because it actually takes more than an hour to run each test. And so they said, hey, do you mind if we come up with our own high pressure pump? And so that's exactly what they did. So they developed a high pressure pump that can go up to 415 megapascals. That's 60,000 psi for us. And had it controlled using a PLC. And boy, it was nice using that. It sped up testing no end. they also said we hate the tooling. And so they developed an improved tooling system. So here's the high pressure hose going into the upper tooling. Here's the bottom tooling that houses replaceable die inserts that we can use for doing bulge forming. And here's a schematic of the tooling. Here are the die inserts. This happens to be for 11 millimeter dies, and we not only did circular dies, but some elliptical dies to see what happens when we have varying loading conditions. So once we started bulge testing, and these are actually done with our original tooling that I showed you earlier, we started getting bulge parts, and we measured the dome height, and we used Marciniak's and Benedict's methods for estimating the material properties, the K&N values for within the plastic regions. And then we also looked at a cross section to see what's going on in the cross section, because most Marciniak's and Benedict's assumes that the maximum thinning occurs at the pole of the bulge. And in fact, we did find that along this region, that pole is where the maximum thinning occurred. However, at the die shoulder, we had a significant amount of thinning too. And we call that thinning a locking region, because we found that the sheet would stop somewhere around here as it flowed into the die cavity. So we wanted a better method for measuring strains. So we developed an electrochemically etched microscale strain grid measurement system. One of my grad students did that as well. And so he looked around, he contacted the Louisiana Accelerator Center, and they had the equipment for spinning SU8 onto workpieces. So he spun SU8, used an SEM grid, and exposed the workpiece to ultraviolet light, and then developed it. He washed away the unexposed SU8 in order to form these columns, which he used as a mask to electrochemically etch grids. And by the way, there is somebody else who used SU8 to produce grids like this, but they had some issues with the grids peeling off, and so we overcame the peeling off of the grids by electrochemically etching them onto the workpiece. So here's a picture of the undeformed grids. We added these little bars here to help make it easier for us to measure this strain. Here's what the grid at the pole looked like after hydroforming, and these scales here are correct, but we also I chopped the figures so that they wouldn't be quite so big, and we measured what the strains were in these sections here. So looking at the strains at the pole, which is for the circular die, where we're going to find the material properties. If we look at the 11 millimeter die, we can see that when we add a trend line, that the trend line is nice and linear. There's actually 3 tests and strain measurements for each one of these pressures, and the agreement is pretty good. So our correlation coefficient is over 99%. When we start looking at what happens with the 5 mm diameter die. You can see again we have pretty good, but not as good agreement between our trend line and our strains that we actually measured, but still really quite good. This one here, this strain here, that was actually right at the onset of the burst. It had not burst, but was about to burst. So we could see, so a little, just a small amount more pressure, and we would have had a burst condition. So we wanted to, while we were using some of the elliptical dies, we wanted to see why this strain is moving down the bulge. And so we did some FEA models. Here's the circular die. Here's an elliptical die with a slightly lower aspect ratio. That is, the major diameter was longer than the minor diameter, and then we had an even more and then we had an even more elliptical tooling here. And you can see that the high strains are up here, and then as we increase in the aspect ratio, we have a shift in the tears further and further down. So at the highest aspect ratio, which was 0.5, we actually were getting our burst, and it shows up in the FEA models of failure right at the die shoulder. So my last case study that I want to talk about is for friction stir extrusion, and that's both forward extrusion and back extrusion. So in the forward extrusion, we're reducing the diameter of the workpiece from 12.5 millimeters to about 6 millimeters. And for the friction stir back extrusion, we're making tubes where the outside diameter is about 12.5 millimeters, and the inside diameter of the tube is about 6 millimeters. So again, we had a problem. We had no tooling available, no instrumentation to speak of. We did not have a dedicated friction stir machine, and not only that, but we had no we did not have access to a CNC mill because that was either down or it was being used by other people almost all the time. We did have access to a 1 horsepower manual Ridgeport mill. And so the only thing we could do is say, hey, let's try it and see what happens. So my students started designing tooling. They had a number of failures, but eventually they came up with a tooling design that was robust and made good parts. So here's one of the early versions of friction stir forward extrusion. And there was the shop technicians said, we are not going to let you use the manual mill anymore because you're going to break our mill. And so I said, well, there's only the one thing to do. We're going to make our own friction stir machine. So here's the friction stir machine. And here's the new tooling that they designed. And originally it was cranked. But it's being automated with the PLC within here. We're measuring forces and temperature for forming. And here's what the tooling design looked like. This is actually our first successful iteration for tooling. This is for back extrusion. We used a 6 millimeter probe. And again, the die cavity to house the workpiece was 12.5 millimeters. So we had to add this top plate, which could float on these pins, and this bushing to prevent the 6 millimeter rotating probe from deflecting too much during the stirring process and have the probe fail due to fatigue. So here's one of our early test samples that we sectioned. This is the top section, just as we're starting to do our friction stir back extrusion. You can see that the grain structure is relatively chaotic. Once we got down to the bottom of the tube, into the workpiece that hadn't been deformed, we looked at the grain structure. We can see the stir zone. We can see the heat affected zone, the thermomechanical zone, and then the base material down here. Looking at, because we were using a flat probe, looking at the corner region, you could see that we had cold cracking that occurred. We also had a void that occurred, and then the base material. And again, you can see the various zones for friction stir extrusion. So the reason why we have cold crack probably is because the shop technicians told the students that as soon as you're done with and pull the workpiece out of the die, throw it into a bucket of cold water. So a lot of thermal stresses resulting in sudden quenching, and so cracks ensued in the workpiece. However, it's absolutely really cool, and we were delighted with the results. And we're in the process of doing more tests with more improved controls on our machine. So we also were interested in forward extrusion, so reducing the diameter of a rod. We found that a number of industries were interested in this process for numerous applications. And so here's our tooling. We changed it out a little bit so that we had die inserts. So now we can use the same tooling for both forward extrusion and back extrusion. We have top plates to help guide for back extrusion. And so here's our workpiece. Here's our hollow rotating probe, shown the cross section is shown here. And here's what happens with the workpiece still mounted within the die, having extruded out, and that's about 6 millimeters, and our initial diameter is about 12.5 millimeters. Here's another picture of an extruded part, another part picture of the extruded parts sticking out of the workpiece. And this was actually this extrusion was actually within the rotating probe, which was hollow. And then my student said, hey, what happens if we use chips? Because this could be, excuse me, great for rotating, for making, for a recycling process. And so here's the extrusion. We did solidify the chips. You can see that right at the center. You can still see a little bit of the chip formation. You can see that down here at the end of the chips, they fused, but they have not solidified to a solid workpiece. Down here, within these two regions, there was chip solidification, and this is just a backer block that was used to make sure that we did not crash into the insert. With this machine, we could measure the temperatures, and so what was surprising is that we only got, for our early tests, temperatures up to a little over 100 degrees. And you can see that our forces, with a relatively constant advance of our probe as it plunged into the workpiece, was somewhat noisy, should I say. That's actually because we were manually controlling the plunge and trying to keep the plunge rate constant by turning a crank. So there was a significant amount of noise due to it being a somewhat manual process. This 100 degrees is surprising, but then we had to think about why this happened. And it turned out that, hey, the thermocouples were about 12 millimeters from the workpiece and located within the die body, the tooling body. So it would take a while for the tooling to heat up. And the other thing that is we found out, and I'll show it to you right now, is that we had variations in we had problems with mounting the thermocouple, which we have now taken care of. But you can see that there was a significant step in this particular test. And so now we're in the measuring within the recrystallization temperature, and we've actually got to test up to 450 degrees Fahrenheit. So well within the recrystallization temperature. And we then started looking at the probes and the discoloration, which we could then relate to the tempering colors of steel. And we found that we were getting up within our visible region somewhere around 310 Celsius. And actually, if you look down here, we are even in this region. So we were getting up to even maybe 388 degrees. The noise is because we found that our friction stir machine had some issues with the guide rods, which were under designed for vibration. And so a lot of this is noise due to the vibration of the guide rods. And we've since this was produced, we have corrected that problem. That's my presentation to you. I want to thank you very much for inviting me. It's been an absolute pleasure and an honor. And here are some references. And do you have any questions?